Hey there, my name is Alejandro, and welcome back for day 194 of me doing the Daily LeetCode challenge that there is 1 year's worth of green contributions here on GitHub. So today is promised for January 26th, 2025. Without further ado, let's get straight into it. Okay, today we get a LeetCode hard problem 2127, maximum employees to be invited to a meeting. A company is organizing a meeting and has a list of employees waiting to be invited. They have arranged for a large circular table capable of seating any number of employees. Okay, the employees are numbered from 0 to n minus 1. Ooh, this looks like a philosopher's dining problem. The employees are numbered from 0 to n minus 1. Each employee has a favorite person, and they will attend the meeting only if they can sit next to their favorite person at the table. Okay. Only if means it points in the forward direction. Employee attend implies next to favorite x next to x. Given a 0 index integer array favorite, where favorite divide denotes the favorite person of the ith employee, return the maximum number of employees that can be invited to the meeting. I see. And this is a LeetCode hard. Oh, dang it. Okay. And this must be done in linear time. Oh, boy. Oh, this is one of those, like, you know, essentially you want, if you think of this as a graph, you essentially want the length of the longest chain. Now, the only thing is that an employee can be pointed to by two people, and that's okay. It's almost like it forms a tree. With that said, just one. One can be the middle one. Everything else, like, you know, it has already one neighbor, so it needs one more. But even then, or how do the ends work? You don't care about who's the second person that sits next to you, I guess. So yeah, so really, if you think of this as a graph problem, you want to know what's the length of the longest chain. We've solved this type of problem before, but I forget how to do that. Ugh. Right, one way is like your DFS from everything. Or you think of deepest chain. Basically, it's a graph where the number of edges is the number of nodes. Really, you just want the largest connected component. Okay, let's do some things. Yeah, no. It was essentially an adjacency list. Okay. Okay, 2 is a big favorite, geez. Yeah, the biggest chain is 0.6. Zero points to 2. Who's 2's favorite? 0, 1, 2. 2's favorite is 1. Yeah. This is the length of the longest chain. Like there's 2 people that can be next to you, right? Like that's implicitly defined from this problem, right? It's like a table. Is it? It's just I'm trying to figure out why this is a LeetCode hard, right? Like before you start getting confident, and there are hints in case we need them. But otherwise we'll do. Do we do like a? What will happen if I do a topological sort? Right, at least I have a topological sort to essentially define heights. There might be cycles in this graph. 1 points to 2, 2 points to 1. Do you want the people that are popular or do you not want them, right? Yeah. Essentially, you want connected components. One way we can do connected components is by DFS, right? Let's just do that. Node to component. This is gonna be an interesting problem. Okay. The other thing is like, yeah, if I visit something that's already in a component, I want to make sure that they all get added to a component. Start a DFS from current node, keeping track of revisited node. If at any point node is visited belongs to a component, it should all be mapped to that component. Actually, since everything only has one neighbor at most, we can, instead of using a stack, we can just do like, yeah. Set. while cur node not in visited. But add cur node. We'll say something like that. Here break. Otherwise here we'll just do cur node equals node loop invariant. Eventually you end up pointing back to something. Print f string components. And we've got nothing. Yeah, well, cur node. Assert cur node visited. Assert cur node node to component. To do might not be true. Or of two asserts. Whoops. Cur node not visited. Okay, let's think here. alert to that. Or is assert current node visited and not a node component? Wait. Here, what we want is like a continue, right? Or break. Break. Continue. I just want to print some stuff right now. Sure. Tack. Visit a node. I just hope that everything is still kept by reference here. No one pointed to 3. Why was 3 in there? Why did 3 get mixed around in there? Okay, so I'm just making one component at this point. It's just weird. Anyways, okay, sorry, I'm being extremely quiet here. My idea is essentially to split this up into components, right? What's the best way to split things into components? Is it disjoint sets? I guess it might be disjoint sets, right? Wait, no, that is what I do want. Where it's like you can figure out if it's something, yeah. Just with disjoint sets, what do I want? Okay, here let's reset. For union, for disjoint sets, union function as well as a find function. Like a favorite. Def find node. Node equals parent of node. Turn node. Yeah, I really need more practice with disjoint sets. But then that doesn't work, right? I have like a million people pointed to. That idea doesn't necessarily work. Right, what I will need though is the biggest parent streak. The problem is that this graph can have cycles for sure. Right. So ideally you want unique connections. So 2 had an in degree of 0. So basically you really want to favor things with a higher in degree. And between that, you'll pick the two other options with the highest in degrees. Okay. They always gotta give a LeetCode hard right before the contest, eh? It's a classic LeetCode moment. Okay. Yeah, 38.5%, eh? Yeah, the point is to find the longest chain. I've had to face this problem multiple times. Each time I forget how to solve it. It's like, I really should remember. Is it disjoint sets? Two things have different parents. What do I do? If I want to sit next to someone, that should be my parent. Here, this is everything points to 2. 0, 1, and 3 points to 2. 2 points back to 1. So you want 0, 1, and 2, or you'll want 3, 1, and 2. You won't want 1, 2, because then you can't go back to 1. If I did disjoint sets, essentially I'd say, okay, 0 is in the same 1 as 2. 2 is 0's child. So 0 points to 2 as a parent. Yeah, it's essentially... Yeah, disjoint sets is not enough here. Because it's not just about connected components. It's about maximum reachability from a singular node. It's just we've solved these types of problems before, and they are always LeetCode hards. It's just I forget the pattern for solving those. Usually they're like, build a tree or whatever. Here it's kind of like a tree again. There's only like, one node per employee lovings. So the number of nodes is a number of edges literally n. Would it be as simple as just do a DFS from each node? Wait, is it really that simple? Because then it's just like you only traverse up to no. There's cycles, but you just ignore those. I mean, that would be the trivial way of solving this. It's just I assume that would be too slow. Dia from each node. Nice. I'll say ver equals node. Where yep too long visited dot add neighbor. That would probably make a lot of sense right there, and that doesn't work really for really no. Why does this not work here? Zero points to 3. 3 points to 4. 4 points to 1. 1 points to 0. So you can point back at yourself basically, and that's no problem. No. Okay. I 0, max length is 4. 1, 2, 3, 4. Okay, from 1, thinks it can go. Oh, I see. Thinks it can go to 0. There we go. Okay. Let's do that. Okay, so here he thinks it can go 0, 3, 4, 1. Now here's the problem. It thinks it can go 2, 1, 0, 3, 4. So 2's neighbor zero, 1, 2, 3, 4. 4's neighbor is not that one. Okay, so it just must be that the last one is that. And favorite of node in visited than that. Really now? No, this doesn't make sense. Like this. Not quite. Interesting. So let's see where this goes wrong. 0, 1, 2, 2. points to 1, which points to 0. 0, 1, 2, 3. 0's favorites. This should not be possible. Two maps to 1. 1 maps to... Wait, why can't you have 2? Oh, you must go backwards. Hey there, so sorry about that. Another recording just finished, one of my Nico 150 recordings, and just popped in the way, so just cutting that out. So yeah, where were we? Visited set is equal to this, yeah. Yeah, the problem is I need this to be circular and so on, and I've been dead quiet just because I've been like super focused, but yeah, because this is going to be a tricky one. It's going to be a tricky one. It's going to be a tricky one. Tricky. This is a maximization problem. It's obvious in terms of a graph where it's not a DAG, so no DP. I don't know about greedy. And it must be linear. Okay. River divide denotes the, yeah. Also, yeah, we do have hints in case we need them. Honestly, I might open up the hints. It'd give me more time to, if I want to do the contest, be able to actually finish this video in time. Give me some time to do a little bit of exercise tonight, just because all I've been doing is recording Nico 150 videos, or also just continue doing Nico 150 videos. Yeah, looking at the hints would be pretty enticing. Or otherwise, I just take, a nice old normal break. The only thing with taking a break is that if I just end up spending forever and looking at the hints later on at night when it's late, that would be kind of unfortunate. Yeah, because it's just, this is tricky. Well, you need, yeah. Does that mean you can't just do a longest path? Favorite of 2 is 1. Right, where's the case where I'm doing 3, right? 2 is next to 1. And then 0 is next to 1. Okay, there we go. Oh, it's not like that. I can't visit things twice. Or is it that I can only visit things once? No, because when I visit one, it's off limits, right? How do you detect there's been a doubling here? Just 2, we visited once. Then we have 1. Yeah, but here I'm checking if the neighbor is not visited then and only then. And favorite of neighbor, not in visited. No, it's just, oh gosh. Ah, it's gonna feel it, but cause you're in love with mine. Stuck in a feeling. Okay, I can't do this. I can't do this. Yeah, okay, I'm running out of ideas, so Honestly, I think it'll be okay. The contest is in 40 minutes, and okay, I think it's okay if I look at some hints. So you know what? This is a difficult problem. It's a hard. I haven't spent too much time yet on the hard, but I can see that, like, there's gonna be some quirks and so on that I'm missing. It's one of those where I'll spend a lot of time. So honestly, I don't mind looking at the hints. So you know what? We'll get started right away with hint number 1. Okay, from the given array favorite, create a graph where for every index I, there is a directed edge from favorite of I to I. Oh, so the reverse direction. The graph will be a combination of cycles and chains of acyclic edges. Now, what are the ways in which we can choose employees to sit at the table? So it's saying to do things in the opposite way. Continue. And there's going to be something else. And so, okay, so that's interesting. So hint number 1 says to essentially reverse the edges in the other way. And then what? Like the one with the most favorites. So, okay, let's look at hint 2. The first way by which we can choose employees is by selecting a cycle of the graph. So find cycles. Okay. Okay. Let's just says we can simply acyclic chains. Yeah, these are the type of things that, like, this is just annoying to think about. So it's like, if you find a chain, another chain, you can connect it. And this is because I didn't even get past the original 3 easy cases. If I did, I'd be, like, waking up to these monstrosities and so on. So yeah, honestly, I'm kind of glad that I looked at the hints earlier. This is one of those problems that will probably take me forever. And even with the hints, it'll just be like, a matter of implementation, which will not be trivial either. It can be proven that in this case, the employees that do not lie in the cycle can never be seated at the table. Oh yeah, if an employee is not in a cycle, yeah, it points to something that's a favorite. Oh my gosh, you have to be in a cycle. Because if I point to something that's my, if I want to be next to someone that's my favorite, that person wants to be next to their favorite. If it's me, cool, but it's a cycle. If it's not, then they need to point to someone else. But if for that to happen, I eventually need to get pointed back to. Ah. So only employees in a cycle can be together. That's very cool. But then why do we want to do favorite of I to I? Point to me. It doesn't really matter, right? Yeah, this is just just doing this so you build an actual adjacency list. Yeah, 2's neighbors are 0, 1, 3. Those are the ones that point to you. Because yeah, the point is if it's a cycle, right? Whether I go one way or the other way, it kind of doesn't matter. But like, I don't like the way that they're thinking about it in this case. Or at least maybe I'm not understanding why that's necessary. Yeah, so you must choose the employees in a cycle. If it's a cycle, great. The cycle starts and ends somewhere and repeats. You can essentially have all those employees, right? So it's essentially the length of the biggest cycle. Idea. Or for these two sit together, they must form a cycle. Or do they? No. 0 can point to 3 and point to 4. They do not have to form a cycle. 4 doesn't have to point back to 0. Oh my gosh. What am I saying? So you need to do both. It's not that we can choose to do this problem this way or this way. We actually need to do both. Oh my gosh. Huh. Yeah, that's gonna be tough. If anything, I wouldn't mind doing this after I exercise. First way. That's big brain stuff right there. That's big brain stuff. You know what? Honestly, I don't mind putting this on, until after. That way, if I choose to do the contest, I can do it. I can exercise and so on. Come back here with a fresher, clearer mind. Just because I haven't moved all day, all I've been doing is LeetCoding all day. Actually, just because I've been doing more videos of the Nico 150 playlist. But that way, I get a chance to just look away from the screen and so on. And even though it's like, I know what I want to do and so on, I just want to come here back when my brain's a little fresher and we could just code this up right away, right? We'll start just DFSing so you can find where the cycles are. That way it's if you ever end up visiting something you've already visited, it's like, oh, okay, I'm in a cycle. The length of this cycle is one possible value. Otherwise, it could be that you never enter a cycle and so on. But it could be that as long as everything is nice and next to each other, kind of like this, then things are okay. And then I'm guessing there's on top of that, they're saying here that you can take cycles of length 2 and combine two acyclic chains. It's just as long as one of the ends are the other, because it's if you have a cyclic chain let's say 0 to 3 to 4, then essentially 4 has a free spot and 0 has a free spot. So if you have two acyclic chains and you have a cyclic chain of length 2 that essentially is able to connect stuff, then great, right? If you have two nodes over here, it's 4 connects to one of them, 0 connects to the other, and there you go. Bada bing, bada boom, right? So yeah, it's almost reminds me of a linked list problem. Hey, well, yeah, we'll come back to this and just put it up later. I just want to give myself a chance to. I might still solve some LeetCode problems, but I'll do some nice and easy greedy LeetCode memes with the Nico 150. Just get back into the rhythm of things, do the contest maybe, go bouldering, and just come back and do this beast of a problem when I've been a little bit more fresh. So for me, it'll be several hours probably, but for you guys, I'll be right back in literally just 1 second. Hey there, I'm back. Okay, it's the very next day. I just came back from pickleball. As context, it is literally 3:49. So I have literally only a little over 10 minutes in order to finish this daily LeetCode challenge. I don't even completely remember what the problem was. Oh yeah, we had these employees that needed to sit next to each other. We were looking at some of the hints and so on. Okay, what I'm gonna do is I'm gonna quickly remind myself what the problem was. And it's 3:50. I'm gonna end up looking at the editorial. So a company is organizing a meeting, has a list of employees waiting to be invited. They have arranged for a large circular table capable of seating any number of employees. 0 to n-1. Each employee is a favorite person. They will attend the meeting. Oh yeah, only if they can sit next to their favorite person. What we were trying yesterday. Oh yeah, essentially try to find the longest sequence of nodes. Okay, only if they sit next to their favorite person. The favorite person of an employee is not themselves. Given a 0 index to the integer array favorite, where favorite divide denotes the favorite person of the ith employee. Return the maximum number of employees that can be invited to the meeting. Okay. Oh yeah, and the hint number 1 was make them. Oh yeah, so reverse the edges. And there was some hint 2s and so. Okay. Okay, hint 1 from the given array favorite, create a graph where for every index I there's a directed edge from favorite I to I. The graph will be a combination of cycles and chains of acyclic edges. Okay, and now what are the ways? Okay, the first way by which we can choose employees is by selecting a cycle of the graph. Okay, it can be proven that in this cycle. So is there always a cycle in the graph? So what is it? Every single thing points to a favorite employee. Is there? No, there doesn't have to be a cycle, right? Well, no, there does. Yeah, because, if I want to try to make it a non-cycle, essentially I create a chain of employees, but I have my start node, and then the last node, essentially the chain, I need that last node to point to someone. If I don't have a chain, then I already have a cycle. And then, yeah, whatever's the last thing in the chain like if I have, you know, node 0 point to point 1, node 1 points to point node 2, 2 points to 3, 3 points to 4. Eventually when you get to n needs to point to something, and whatever it points to, it'll essentially create it. Okay, so there's always a cycle in the graph. Okay, cool. It can be proven that in this case, employees that do not lie in the cycle can never be seen at the table. How do we do cycle detection? Like, I know, well, it's not about whether or not there is a cycle or not. It's about actually finding the cycle. Okay, I have less than 8 minutes. The second way is by combining 2 seconds. Okay. Let's look at the editorial and just try to do something. I don't want to lose my streak. I know this is a little bit unfortunate because I won't end up solving this problem myself. Jesus Christ, what is this? What? Holy crap! What is this explanation? Given the number of people the company hopes will attend and each fair, we must return the largest number of people who can attend while sticking to the requirements that each person must be seated next to. At this point, we can observe that the problem can be seen as a directed graph where each employee points to their favorite person. The key observation here is that this graph has cycles. True, and those cycles are important because any group of employees in a cycle can sit next to each other in the meeting, so detecting these cycles will be central to solving the problem. However, we also need to account for the fact that there might be chains of employees not forming cycles by themselves, but who are connected in such a way that they can potentially be linked from a... We also need maybe chains of employees, sure. What do you mean not forming cycles? There has to be a cycle. Or do they mean like essentially I have like a chain and I pointed to somewhere and then whatever was up here in the chain or something? But what are connected in such a way that they can potentially be linked from a larger cycle? This gives us the idea that even if a group of employees doesn't form a cycle initially, it might still be part of a larger group that can be arranged in a circle. Okay. A final thing to note is that the circular nature of the seating arrangement may influence how you connect the employees, especially when identifying groups or cycle. They can sit next to each other. We have 2 main types of structures that can... Okay, I have like 6 minutes left. Oh my gosh. A one-way connected cycle, this is where employees form a directed chain like A, B, C, D, A. Okay. This means that the person's favorite is part of a larger cycle. Everyone must sit next to someone else in the cycle. These cycles will only be able to seat as many employees as the cycle size. A mutual two-way cycle. In this case, people like each other mutually, meaning okay. This is a two-way connection forming a two-cycle group. These types of cycles allow us to put more people on the table because we can treat them as a smaller unit that can connect to other parts of the graph. Oh, I see, because if they point at each other, then you can arrange them to anything else, right? Because otherwise, if like, you know, A pointed to something else, then it's like, okay, you have B, A, and then A points to something. But now because A points to the guy that points to him, we can include both of these and then make this connect to something. Okay, let's go over the examples to break this down more clearly. Example, oh my gosh. Okay, we can visualize this graph where each node has an edge pointing to their favorite person. Person A likes person B. We can construct an edge from A to B. Then we can construct the graph as follows. Okay. Oh my gosh, okay, sure. Cycles with size greater than 2. Green cycle. For cycles like this, no additional employees can be added to the cycle because everyone must sit next to their favorite person, and adding cycles would disrupt that. For instance, in the cycle, okay, so if you have, for some reason, a greater than length 2 cycle, then you can't add anything there. But if you have a cycle with size 2, meaning 2 things point to each other, then essentially you can connect stuff. How do you connect stuff? For these types of cycles, we can have 2 multiple cycles sitting next to each other. These cycles can connect with extended paths, chains of employees, as long as they don't disrupt the seating order. For example, oh my gosh, this is so long. Okay, am I just gonna end up having to copy? Oh my gosh, this is so long. Holy crap. Okay. Oh my gosh. Cycle detection with extended paths. Jeez. Oh man. Topological sort to reduce non-cyclic nodes. "46 lines of code. Okay. I see. 1.5 hours. Okay, people are good. Yeah, mine is about to end here. Well, I have literally 3 minutes left. Unless it's for some very specialized row. Oh, this guy's a YouTube video on it. Cool. Yeah, okay. Maybe we can copy like one of the solutions and try to understand it. Okay. Alejandro. Attempt. Failed attempt. Here we'll say solution from editorial, using it to not lose my streak. Okay, so if we run this, this will work. Yeah, okay. I feel guilty for submitting this. Yeah, okay, so like completion streak 194 days, consistency is key, see you tomorrow. Yeah, okay, this is super unwell deserved. By the way, if you just got to this part of the video, it is literally between 2 and 3 minutes left until the very next daily challenge. So here I just took the solution from the editorial and pasted it in here. But I want to make sure that, okay, even if I don't end up solving this problem myself, at least, you know, trying to make sure that I understand what's going on. So now that we have a solution in there, okay, I can relax. I didn't lose my streak, although the problem will go away soon. Although, okay, I guess I could just stay on the problem and just relax, right? I can continue working on this problem and so on. Okay, that's fine. That's fine. I just didn't want to lose my streak. Okay. Here we'll say yeah, I brought a bar that I was eating on the way, but I didn't finish it because I just wanted to get here as fast as possible. Okay, let's continue reading. We can have multiple 2 cycles sitting next to each other. Oh, true. This can sit to that. Oh, well, that's very cool. This is a lot of stuff for one problem. Oh my gosh. 0, 1, 2, 3, 8, 9. 0, 1, 2, 3, 8, 9. 13, 12, 11, 10, 14. I see. So length 2 cycles are really OP because you can append them to stuff. Well, I guess, okay, you can't append them to a green circle like this. So you can chain length 2 cycles in a really large way. Oh, and this is why they're gonna reverse edges. It's like if you reverse the edges, it's like doesn't matter, it'll still be a closed cycle here. Here, obviously, for length 2 cycles, it doesn't matter if you reverse edges. Or something like this is like if you have a length 2 cycle, you can start exploring like, you know, what is the deepest path this way and deepest path this way, kind of a thing. But that's like out of all the length 2 cycles, you need to be able to essentially grab the one that has the biggest expansion. Or you can connect their expansions together. Right, if this expands to like 24, 25, instead of connecting things with 8, 9, you expand it with 24 and the 25. Oh my gosh. Okay, so it seems like every connected component of the graph includes a cycle. If it includes a length 2 cycle, you can start chaining the hell out of it. In fact, you can chain each group that only has a length 2 cycle. Or there's also cycles that maybe right here you can chain 13, 12, 11, 10, 14. And next to 14 put 8 and 9. Next to that put 1 and 0. And next to that put 3 and 2. holy crap, I have no idea if I would have actually realized that if I spent a long time. At least it would have taken me hours and hours and hours to figure out something like that. Oh my gosh. That is so cool. Oh my gosh. Okay. Okay, so what is this one complete? Oh no, this is a length 2 cycle. Wow, so it connects like this. Here's the length 2 cycle. Connects like this. Oh, but these are not length 2 cycles. Right. I see. So that's why you're going to invert the edges, because from the length 2 cycles, you want to essentially expand as outwards as you can. So you want the edges to go in the reverse direction. This is really insane stuff. Okay, like in a problem like this, you do not solve this problem unless you draw things out. So maybe I should learn to just, draw things out, because this is actually impossible unless you draw things out. And you need to get lucky and like, think of examples like this. Because like, how do you start thinking of like 2 seconds? Okay, I'm not convinced at all that I would come up with stuff like this. Holy crap. Maybe I got kind of lucky that this is the LeetCode hard I chose to, like, by the way, for reference, like the reason I did this is, yesterday I got really sad because I wanted to play pickleball in the morning and like do LeetCode at night, but I started doing like LeetCode in the morning and so on. It was already afternoon, so I started doing more LeetCode, and it was already dark, and I just kept doing LeetCode and so on. I did the contest and a whole bunch of LeetCode 150 problems. And because I wanted to get through like some of the sections, so like right now I'm in the section that is greedy, and I got a little bit stuck on the very, very, very last greedy problem. I think it's like if I come here, like I'm on valid parentheses string and so on, not because it's like insane or whatever and so on, but it's just taking me a little bit of a tiny while, and yeah, so yesterday was like a lot of LeetCode, and when I woke up this morning, I was debating like, okay, do I do the daily or do I go play pickleball, because I don't want to waste a morning again. I ended up choosing to go play pickleball and so on, and I lost track of time, and I came back and it's just like literally 10 minutes left for the daily. Like the bus took 15 minutes to arrive and so on, but okay, excuses are excuses. I don't want to blame anything. Like this is completely my fault. I just wanted to explain kind of context of what's going on and so on. Like this is the very, very, very first time that I do this on a daily LeetCode challenge, where it's like I don't, I've gotten to the point where it's like I saw them the next day, but never where it's like I wasn't able to finish it, whether or not I solved, or the very, very rare few times where I had to like look at the editorial, which I think I can count the number of times that's happened in like in the size of one of my hands. But yeah, this is definitely probably the most failure of a daily LeetCode challenge video out of all my videos so far, which is a bit unfortunate, but yeah, okay. If there's one to do it on, this is probably the one, because this kind of looks insane, right? Where it's like, yeah, it's always this is something that I realized in college. It's very deceptive with hard problems inside of any subject, where it's like understanding a solution is oftentimes much harder than actually coming up yourself. And even in computer science, there's kind of that phenomenon. Not really, but like if you think in terms of like NP complete problems, it's like they have polynomial time verifiers, but no known polynomial time algorithm to solve. So it's like it's very easy to check if a solution is correct, but very, very, very hard to actually find a solution yourself. Obviously, that's the difference. But I kind of like using that little analogy where it's like. Yeah, oftentimes, understanding a solution is much, 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 much easier than coming up with a solution yourself. And this is probably one of those problems. I'm not going to even pretend that maybe this is something that I would have figured out. It would have taken me at least a long time. Like, I don't know how you start going in the path of like, I guess, okay, like as I came back, I started realizing like, there must be a cycle. Maybe I can like start thinking about those cycles more. I don't know if I would have started thinking about chaining and stuff. Like that's a lot of details. Maybe just because we got the hints, right? Maybe because of the hints, I'm able to like start slowly building context cues. But yeah, so I definitely need the hints. But even then, I think it'd take me a really, really, really long while. Okay, so let's keep going. Yeah, so here's like, okay, we have a length 2 chain here. Yeah, we'll need to invert the graph for sure for this. So, and so if there's a closed cycle like that, so, I'm guessing from their definition, I don't necessarily understand the proof for it, but I'm guessing, okay, if there's more than a length 2 cycle, yeah, let's think of a length 3 cycle. It's like a triangle. Everything, so you point to something and something else points to you. Essentially, your two neighbors are already chosen in place. There is no ability for you to chain. That makes sense. So if there's more than 2 elements inside of a cycle, everything's 2 neighbors are defined, right? For 7, its 2 neighbors are defined. 4 is its favorite and 6 is its favorite, which is eventually pointed to by one of 4's favorites, right? So it's like, okay, if the cycle is greater than length 2, then there is no ability for you to chain things, right? You can't put something next to the 4 because it's already next to the 5 and the 7. Okay, that makes sense. See, okay, that's genuinely cool. That's actually cool. And yeah, if you invert the edges, it doesn't matter. The cycle is still there, and for like 2 cycles, they're still there. But it does matter when it comes down to chaining. Damn, that is really cool. But even coding this up is not easy. Okay, so I'll be curious. Okay, this is cool. This is a cool problem. By the way, if I refresh, we'll see. Like, see, I'm not capping. Like, there's a new daily in here. So, yeah, like we're doing the slate. We're doing the slate. Okay. Okay, well, we were here. Okay. Yeah, in this example, there are more complex cycles and paths to consider. We need to find the longest possible extended paths for each endpoint of a 2 cycle and combine them efficiently. Yep. But you can always combine them, right? What do you mean efficiently? Can't you always combine them? For instance, for the 2 cycle, 1215, blue rectangle, we need to find the longest paths from each of those employees. Starting from 12, we can trace the path, 18, 4, 22, 7, yeah. So you invert the edges so they can DFS from the 12 to the deepest thing you can get, right? That is not in the direction to the 15, right? Yeah, so don't go to the 15, obviously. Right, because when you invert these edges, like one of 12's neighbors is still the 15, but that's part of the like 2 cycle. So you want to go this way. Holy crap, this is really cool. A lot of details, which often makes, I mean, this is a LeetCode hard after all, but if anything, I'd call this maybe like a super hard, right? Like there's some LeetCode hards that are like, bruh, okay, UCS. And it's just like, all right. And then there's some LeetCode hards that are some what I call super hards. Okay. Yeah, okay, I don't know. This is maybe I should start like there's been like exponential time hards, and this is like NP complete hard, where it's like hard to do, maybe easy to understand. Well, not because it's legitimately NP complete. I'm using that as an analogy here. Okay, anyways, enough babbling. And okay. Extend, yeah. Connected to a cycle, forming larger groups of people that can sit together. So our core solution consists of 3 parts. Cycle detection. Oh my gosh. Since every node points to exactly one other node, the favorite person. Yeah. Yep. I see, yeah. DFS from a node, essentially the very first node that revisits itself, we can consider the start of a cycle, right? Because the point of a cycle is a cycle. So the very first node that we hit, no. It's interesting, right? Because it's like here, if you DFS, right? If we have the arrows pointing the other way, right? There's always at least one cycle in the graph, right? So in this case, if you keep the graph in this way, you'll always end up being able to detect a cycle from a singular DFS, right? So maybe we originally don't invert the graph to essentially find all the cycles, and then classify cycles in terms of, Jesus Christ. Okay, so we can classify them in terms of length 2 or greater than length 2. For the greater length 2, we can again rerun them from the nodes that we visited that the cycle starts at to get their length. Man, even understanding this solution, this is a lot of details. This is a lot of details. Okay, so we need, since every node points to exactly one other node, by walking through the graph, I'm going to explore nodes and stopping when we visit an already visited node. This works well because each node has at most one ongoing edge, simplifying the process. So yeah, so we can essentially have like a set of unvisited nodes. Essentially, the very, yeah, so that I can do, right? The way that we'll do, here we'll call this editorial. The nodes are range I to n, right? 0 to n minus 1, right? Visited equals set of range. Well, node not visited, then node isn't visited. Print f string cycles equals 0 negative 1 for now. And do something like this. Here we'll do n, like the favorite. Bring up that brightness a little bit. It's just interesting. Yeah, this is just weird. It's just like it's in like multiple cycles or something. Yeah, okay. Yeah, thank goodness I'm looking at this editorial. Honestly, I'm just gonna try to understand this solution and call it a day. Find the longest path. Once we have detected all the cycles, we need to handle two cases. Single cycle with size greater than 2, we treat it as a unit. You can't add more people. True, sure. Multiple 2 cycles. We look for the longest extended path for each endpoint of a 2 cycle using BFS or DFS to find the longest path starting from the mutual favorite. The maximum possible length for any group is the sum of the longest paths from both endpoints plus 2. For the mutual favorite thing people themselves. Yeah, 3 plus 2 plus 2. Yeah, makes sense. And then you can chain them all together. Final comparison. Once we have the from the max. Yeah, so the longest from closed cycles and the longest in terms of chaining 2 cycles. Okay. There'll only be one value for the chaining of the 2 cycles. Out of all the closed cycles, we'll take the max of those, and then we take the max of that. Okay. Sure. Okay, cycle detection with extended paths. Okay, from the overview, the problem boils down to identifying cycles in the directed graph, determining how chains can be connected, ensuring that employees are seated next to their favorites. To implement this, we first need to create a graph that represents the relationship. We're constructing a reverse graph where each person points to the people who have them as their favorite. Makes sense for the This completely makes sense to me now. This structure allows us to easily trace back to the people that led into each person's chain. 100%. Next, we iterate through the graph's nodes. If a node hasn't been visited, okay, so yeah, here what we'll do is first of all, we'll get rid of this. Yeah, we'll just get rid of it. Here we'll say n is equal to length of favorite, sure. Here we'll say adjacency list is equal to default dict of list for line range n. Why is it so weird? What? What? Okay, I'm just gonna restart. Okay. N is equal to length of favorite. Adjacency list equals default dict of list. Line range n. Adjacency list of so I points to favorite of I, so we'll have favorite of I dot append I. A string adjacency list equals return -1. Yeah. 0 does point to 2, 1 does point to 2, 3 does point to 2. 2 does indeed point to 1. So yeah, we have everything reversed. So we can chain components with length equal to cycles. With length 2 cycles. There you go. Next, we iterate through the graph nodes. If a node hasn't been visited, we start a traversal, tracking visited nodes and the distance from the start using a map. Distance from the start. It's visited during the traversal. We've detected a cycle. Oh my gosh, this is like find duplicate number level stuff. Oh my gosh. Okay. Man, it's so cool the way people think. Okay, honestly, I'm glad that we're doing this. Honestly, this is maybe like destiny, right? Where it's like I just get to learn new LeetCode tricks just by reading this editorial. This is good. Yeah, so here we'll do the very same thing. Unvisited is equal to set of range of n. While length of unvisited is greater than 0. Here, like, what I want to do is I want to make sure that I don't look at the editorial code. I'll understand what they're telling me, but write my own code. While length of unvisited is greater than 0. There's that, I can't fathom, like, the amount of detail that is behind this problem. Like, holy crap. Like, if you're given this in an interview and you saw it, like actually, bravo. Like, I'm honestly stunned at, like, the fact that, like, people come up with solutions like this is so, people are clever. People are very, very clever. While length of unvisited is greater than 0, here we'll say node is equal to unvisited.pop. Here we'll have node to dist. Equals 0. Node to dist equals current distance. Favorite of node. Current distance plus or equal to 1. Assert node in node to dist. Cycle length is equal to, holy crap. Like, holy crap, people are just giga chats. Like, okay, a node to like actual giga chats. Okay, it's so, I love people, man. Like to be this smart, that's cool. That's like, it's very cool. Okay, cycle length is equal to current distance minus. Right, let's think about if it's a length 2 cycle, right? So here I'll go to the favorite node. And I haven't gone there. Over 0. Now I'll go back to the original. Right. Let's think, right? Here this will be that. Now essentially, this will be minus node to dist of node. Essentially, node to dist. Like, let's say that there's, like, 1 and 2 point to each other. Then here I have current dist. So 1 is not in there. So, node is equal to 1. 1 is not in there. So here we'll say 1 maps to 0. So, yeah, node is equal to 2. Current dist equals 1 now. So then we'll say 2 points to 1. Great. Node to dist 2. Wait, so yeah, 2 points to 1. Node is equal to favorite node, which is 1. Current dist equals 2. And then now 1 is indeed here. And then when we do 2 minus 0, that's perfect. It is a length 2 cycle indeed. So that is indeed the length of the cycle. And then yeah, if we obviously had, like, 3 points to this and so on, like, we'd only get to here, and it's just like the 1 would be at 1 here, but the current distance would be 3, so it's still length 2 cycle. That's genius. That's genius. Very trick makes sense. It's just like, again, it's just I love learning these type of tiny little tricks and so on. It would have made problems like find duplicate number a lot easier when I did them. Which is from the Nico 150. Okay, we've detected a cycle. The cycle length is a difference distances at which we encounter and revisit the node. I really hope that today is not another LeetCode hard. Like, please have mercy. Have mercy. Okay. A cycle length greater than 2 forms a self-contained group, which we compare with the largest cycle found. Okay. Oh, wait. Yeah, we've... Oh, that's true. Oh my god, wait. We're going to be able to do things very, very simply, right? Here we'll have a res equals 0. If cycle length greater than 2 forms a closed cycle which cannot be chained. Hence, right, the very worst case, we can't fit any employees, so res should be 0 initially, right? If cycle length greater than res equals cycle length. If cycle length continue. Right, otherwise assert cycle length equals 2. Right? Yeah, and the convenient thing is that there's always a cycle in every single component. Like, this problem is so, like, wow, it's like things fall in place perfectly, mate. Holy crap. Assert cycle length is 2. Now, we will want to perform a BFS for longest path between each ends of this length to cycle, not allowing through the other node in the length to cycle. Okay, for now, okay, we'll come back to the editorial if we need it, but I think I understand enough where it's like I know how to solve the rest of this problem for now. So we'll quit away from the editorial. If we need it again, we'll go back and so on. But like, yeah, this is just very, 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 very cool. Okay. Now we will want to perform a BFS for longest path between each end of this length through cycle. And use and remember result as will allow as it can be chained with other length to cycle components with length 2 cycles. Length 2 cycle components equals this. Or we can have it as a current number. Length 2 cycle chain equals 0. And here we'll return length 2 cycle if res less than length 2 cycle chain, res equals length 2 cycle chain, return res. Right? That's kind of the idea. Okay, here we need the 2 nodes in the cycle. Step 1, we need the 2 nodes in the cycle and mark them visited. was to not permit each one through the other. Okay, wait. Node is the thing. Okay. We know node is part of the cycle. So the length to cycle must be node and favorite of node, right? Cycle node 1, cycle node 2, equals node, comma favorite of node. Or cycle nodes equals node and favorite of node. Cycle node in cycle nodes. Holy crap. Equals 2 for the 2 cycle nodes themselves. Initially 2. We'll say want to find longest chain. Adding cycle nodes as visited first equals set of the cycle nodes initially, and then we'll say Q is equal to collections.deck starting with longest chain is equal to 0. Do we start it as 1? Or no, if I find... no, I should start it as 0 because I've already counted 2 here, right? So the longest chain starts with 0 from here. Okay. Otherwise, I could start it at 1 if I wanted to make this 0 initially. Geez, this is a lot of things to think of. Okay, visit equals set of cycle nodes. Q is equal to collections.deck. I'm honestly glad that I looked at the editorial. I think this would have taken... I don't know if I would have came up with this myself anyways. So good thing that I'm looking at the editorial early. Even looking at the editorial, it's like, you know, a lot of thinking that goes behind this and so on. Yeah, I'm going to give this... I'm going to give this a problem I like just because it's just like... Because I looked at the editorial, I'm like, wow, I can appreciate how cool the problem this is. So yeah, here this will be... this will be a tuple 0, comma cycle node. So this will be the cost and the node. While length of Q is greater than 0, we'll say cost, comma chain length, comma node is equal to Q.pop left. Chain length greater than longest chain. Really, I want to say if longest chain less than chain. We'll say longest chain equals chain length. And then yeah, now this is when we want to consult the adjacency list. This is when we want consult the reversed edges adjacency list we built earlier Find longest cycle nodes. Into widthwise. Okay. Here we'll say for neighbor in adjacency list of node, if neighbor in visited, continue. Otherwise, he will say q.append and visited.add the neighbor. We'll add the chain length plus 1 and neighbor. Okay, q.append chain length plus 1 and the neighbor in there. Right? And here we'll say length to cycle chain plus or equal to longest chain. And then here here length to cycle chain should really be called length to cycle component. And then this longest branch. And now length to cycle chain. Now chain this length to cycle component chain of length to cycle components. Cycle chain plus or equal to length to cycle component. Right? Is this enough? Okay, first of all, let's just run it and see where we have errors. Yep, yep, yep. Tack, tack. Yep, so we've got errors here. Okay. Yep. First of all, print f string res equals length to chain equals dot append this. Here we'll do sum. For now, we'll just do sum. Is equal to an array. For now, I'll just do sum. This one really doesn't have any length. 2 and 1. I see. No. Oh yeah. We need to get rid of all the unvisited. Yeah. Everything we visited. do this. Can we do something like that? Why do we have things? Why are we able to visit already unvisited stuff? It's just so weird to me. I mean, for now, I'll just do discard. 6, 6. Really, so that's not enough. What happens if we've already visited a cycle before? How are we? Oh, I guess a cycle might have multiple entry points. You won't say already seen cycle. Okay, if it's a link, okay, wait. No, we can't do this, right? If it's a link to cycle, okay. First of all, the easier case, if it's not a link to cycle, then it's a closed cycle. So it doesn't matter this other thing that points to that closed cycle. It's irrelevant. Now, if it's a link to cycle, it's fine because we'll end up visiting the longest path from there, which might include the nodes that we just saw. So this is fine. This I would expect to be all right and to be bing chilling, right? What is the response for this? Oh yeah. Otherwise, we assert this, and we say that. And now we're bad. The first node is already... Now we'll do this here maybe. That way we don't consider this guy over here. Weird. Very weird. Or maybe we put this here. It's just weird. very, very bizarre. Yeah. Okay, first of all, if I get rid of this, yeah, the problem is that I have 0, 1, and 3 all point to 2. 2 points to 1. It's like I have those 3 and I have this. No matter which one I pick, I'll end up finding the 2 and 1 cycle. And at least 1 or 0 or 3, if not both, will refine the same 2-1 cycle inside of it. But we want to ignore those cases. Right, we should be able to just put this up top and only have that node discarded. Or discard them all and have this down here. If node not in unvisited, what does this mean? If node's been visited. It's just weird. What do we do if we've already seen a cycle, right? If we've already seen a cycle, we already have it handled. Do I put this like down below this if statement here? I see. But does that work in all cases? Wait, why does that matter? Okay, first of all, let's try submitting this. Too slow? Wrong answer. What if I break here? Yeah, because now I don't see the length 2 cycles. Like, what the hell? Yeah, of course this is wrong. It's this though. It's like, okay, maybe. Okay. I think I know a janky solution. Because okay, if we revisit a close cycle, that's fine. We'll get the same result anyway. It just, yeah, it might be annoying in terms of time complexity, but then it matters when we see the length 2 cycles. It's like we keep chaining them. Now we can uniquely identifying them, right? Visited length 2 cycle. Nodes equals set. cycle nodes, call node in continue. Otherwise, right, okay. Yeah, that makes sense. Okay, let's submit this. Even though it's slow, let's just see if it works. I just want to see if it works. Okay, now we're TLEing. We're TLEing. We're TLEing. Okay. First of all prints can become hashtag prints. Is it just those two? No, okay. Okay. Jesus Christ, this is a lot of stuff. Okay, first of all, I mean, I guess this is not really the reason why we're going to TLE, right? Res length to cycle chain. Zero. Actually, here, we'll call this visited cycle nodes. Visited cycle nodes. Or visited closed cycle nodes. Actually, it doesn't matter in this case, because we're gonna look at the or here we can do something like this. Visited. Here we can say visited nodes is equal to a set. Or even just call it visited. Visited.add node. I gotta think about this. Or maybe, what I don't need is this. Right here, first of all, let's remove this test case. Let's just Okay, okay. Yep. He will say for visited node, can we do something like that? Right, and now if I use this test case, are we chilling? Mate, okay. We are chilling. Okay, we are chilling. We are chilling. Are we chilling? Yo, okay. I take that as an absolute win. Okay, absolute win. I don't care that it's slow. I do not care. Yes, we looked at the editorial and so on. Okay, but I looked at only what I needed and I didn't read the rest of the thing. I did not look at the actual code of the algorithm. Obviously, they're going to have something way cleaner, whatever, blah, blah, blah. But okay. I looked at just what I needed to know. I did not look at the editorial code per se. I just looked at the beginning of their explanation, and once I had enough information, I was like, let's stop looking at the editorial and code it up ourselves, right? Yes, it's mega slow, but I don't care. I just wanted to be done with this problem, and that feels like an absolute win in my book. Here I can get rid of this. Yeah, so here we definitely can get rid of the sum. Here we can definitely get rid of the sum, right? Yeah, so here we can make a few things faster, right? Does remove work? Okay, it's discard. Unvisited equals unvisited dot intersection. Here let's open up something. Python 3 set dot add set dot discard set dot diff, yes, dot difference visited. Aha. Can we just do that? Okay. That might make me a little bit faster. Not really, right? Holy crap, this is a lot of code in there. Now we're at TLE. What? How am I at TLE now? What? This is nonsense. That's slower than the difference method? I mean, the difference method is slower than the other one? Really? So if I do it this way, this is faster? Oh, and I guess I gotta get rid of... What? Interesting. Good to know. Cool. Okay, good to know. Yeah, that actually makes me slower. Well, first of all, we definitely don't need both. Here you can say unvisited dot discard neighbor. And here you can say unvisited dot discard node. So it makes things a little bit faster there. Here we'll say unvisited dot discard node, and this works as well. Okay, submit that. So that way I don't have to loop over every single thing all the time. Nice, but yeah, it barely makes a difference. Okay, I don't mind that I'm this slow. It's fine. I will take this any day of the week because it makes my solution feel more like my own. Even though I looked at the editorial, like I'm much happier doing this and having a much slower solution than just copying the editorial, which is just nonsense, right? Just like copy pasting the editorial solution itself. I ended up looking at the editorial, but none of the code, and that is much more cool. Okay, here we can get. We can get rid of this. Yeah, so let's get rid of all the unnecessary comments. For this in range n. Yep, nice. Nice. I see. So is that maybe faster? Wow. Okay. There we go. It's because of this. It's because of the fact that this already seen cycle is false. Original node. Unvisited node. Here we can do dot remove. Can I do something like set dot first, set dot get, set dot help, set. Ah, oh my gosh, I did not know that help. Dude, I'm gonna use this function forever in Python now. And contains equals. Oh, I see. These are private methods. Add, clear, copy. Pop, remove. Yeah. Update. No, is there no get method? Right. Here we'll say node is equal to this. Original node equals this. Equals original node, comma 0, current distance is equal to 1. Node is equal to favorite original node. There we go. Already seen and computed cycle. No need to worry about it again. If it's a closed cycle, we've already compared that cycle's length. And if it's a length 2 cycle, we've already added it onto our chain. Right, and now there's no need for this guy. Right, this I can get rid of. This I can get rid of. Beautiful. Okay. And now we don't have a 5000 ms solution. This is actually great. We're making a thing faster one step at a time. Or here we can say node is equal to this. Note that this is nothing. This is 0. And here, if node not and unvisited, already seen cycle is equal to true. And now we gotta do discard because of this guy. And now it's wrong. Oh, because we've already discarded it. Ah. That's why that wasn't working earlier. It all makes sense now. It all makes too much sense now. What? What do you mean on a network error? What's going on? What's going on? Okay, beautiful, 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 beautiful. Unvisit is equal to set of range n. This is great. This is fantastic. I can call this node. Node. There we go. Now we just gotta clean up more stuff. go. We can get rid of this. Yeah. Here we can't do a remove. Yeah, we probably can't, but yeah, it's all right. Oh yeah, because it'll be okay. Like again, if it's like multiple paths and like one way is getting there, yeah, that's fine. That's fine. Now we can get rid of that. Okay, a nice, beautiful 85 line of code solution. Okay, so we can submit this one last time. And there we go. Okay, 341 ms and so on. Maybe if we submit a couple times, we'll get around the standard deviation curve over and over. So yeah, so we're right in this standard deviation curve. I guess like people, like there's the other editorial solution where maybe this is where people get to hear and so on. But honestly, I'm happy I was able to solve this problem. Not on my own. I did end up having to look at the editorial, but at least I didn't copy paste the code and so on, and I only looked at just enough of what I needed in order to solve this problem in a timely manner. So as always in my videos, I do a quick recap if I was able to solve the problem. So for this one, it was honestly, this is a very, very tricky problem. I was not able to solve this on my own. I ended up coming back here just 10 minutes before the daily was over, which is why you see that here it's like, I don't have a streak because this is for the next Daily LeetCode Challenge problem. I ended up needing to look at the editorial, obviously, because I only had like a few minutes left. And this is kind of a crazy solution. And since it's coming from the editorial, I'll just try to keep it brief. But essentially, I'll give like a brief summary of how this works. The thing that you had to recognize, also my friend Noah, I think, is spamming me through Discord, so I'm just going to quit that here. The thing to recognize here is that essentially you want to set employees, right? Now, there are two types of cycles that you can have. You can have cycles that are length 2 and cycles that are of length greater than 2. If a cycle is of length greater than 2, first of all, first thing to recognize is that the graph maybe has more than one connected component, right? Where it's like, favorite of I and so on. But every connected component of the graph, even if it's just one connected component, has a cycle. Every single one. Every single connected component of the graph has a cycle. Why? Think about it, right? If let's say you want to make sure that, like, okay, I would say, okay, I don't want a chain of the graph to have a cycle. Okay, I don't want a component of the graph to make a cycle. So if I have A here and I have B, I can't have B point back to A because that would make it a cycle. So it's like, okay, it'll point to a next node C, right? And then C, I can't have it point to B or A because otherwise it'll make a cycle. So it's like, okay, I need to make it point to a new node, right? And then D, I can't make it point to any of these because otherwise I have a cycle. So I need to make it point to a new node. And so you see the problem here, right? Every single time I need to make it point to a new node. There's a finite amount of nodes in the graph. So eventually, whatever is the last node here, right? Let's get to Z here. Eventually this Z will have to point back at one of the old nodes. And whichever node it points back to, let's say this B, all right, there is now a cycle that goes from B to Z over here, right? So, which means that, like, A might not be part of the circular loop here, but inside of any connected component in the graph, there will be a cycle somewhere in that component. So that's the very first thing to realize. Now, the second thing that matters is whether the length of that cycle. So obviously, well, one thing they tell us is that the favorite person of an employee is not themselves. So you cannot have a length 1 cycle, right? So the minimum length cycle that you can have is a length 2 cycle. And this is actually very interesting because the only cycles you need to care about are length 2 cycles and cycles of length greater than 2, right? Because here's the thing. If you have a cycle, let's start with the easy case, which is the cycle that is greater than length 2, right? Here's the thing. Let's say the smallest possible cycle that is greater than length 2 would be length 3, right? So here we have A points to B and points to C, and then C points to something like C points to A, right? So like, it goes all the way back here to the A. Essentially, no employees can go inside inside of this cycle is my claim, right? Because here if I have A, and I have let's say like this, and here's my B, and here's my C, right? Each of these guys in this length 3 cycle have 2 employees that are next to them, right? Here, like B is next to A and C. So it can't be next to anyone else because it's already next to 2 people. A is already next to B and C. So it can't be next to anyone else because it's already next to 2 people. And C is next to B and A, so it can't be next to anyone else. So it must be, it cannot be connected to new people, right? And here it doesn't matter, like, you know, how many times you increment this, right? Let's say that we make this over here, we make this over here, this, right? Let's say that instead of 3, we now have 4 people. Doesn't matter. A is still connected to 2 people. D is connected to 2 people, A and C. C is connected to 2 people, B and D. B is connected to 2 people, A and C, right? Since everyone is connected to 2 people, you cannot introduce any more employees inside of this group of employees because they're all already sitting next to 2 people, right? So, if your cycle length is greater than 2, then each employee in that cycle has 2 employees that they need to be next to that are already in that cycle. So you cannot introduce any employees outside of that cycle into this group of employees inside of the cycle, right? So for every single cycle of length greater than 2 in the graph, those employees in that cycle can only be together, and that's it, and with nobody else, right? And so you want to consider cases where it's like, okay, for every greater than length 2 cycle that I have inside of my graph, I am going to essentially consider like having just those employees, because I can have those employees and no one else. So okay, if I have just those employees, how many employees are there? That's a new maximal possible case I can consider, right? So the very first thing is to essentially go over every single cycle of length 2 that you can of greater than length 2 that you can have. Now here's where things get interesting. Sorry, I have like something stuck in my throat. I'm trying to get out and drink with water, but I can't seem to get it out. Otherwise, okay, if you have a length 2 cycle, here's the thing. You can chain them infinitely. Why? Okay, the problem with these length greater than 2 cycles is because for each node you have something that points to it, and this guy points to something which will eventually go and find its way back to the thing that pointed to itself, right? So essentially the 2 neighbors of every single node in that cycle are already defined. Now if the cycles of length 2, like for example this 1 and 0, then we have free reign for whoever we put next to 1 and free reign for whoever we put next to 0, right? Because it just must be that 0 and 1 are next to one another, but like whoever's, like, you know, to the left of 0 must be 1, but to the right of 0 could be anyone. And then for 1, to the right of 1, you know, it must be 0. But to the left of 1, it could be absolutely anyone, right? So I could make one chain, right? I could take this 1 and this 0, right? And then I could chain this up and take this, like, you know, I have this 3 and 2 here, right? And here I can put, I can set the 0 next to the 3, for example, right? Because here I put the 1 next to the 0, which is also pointing to its favorite, great. I put the 0 and the 3 because might as well put them together, and then this 3 is connected to this 2. So I just created a length 4 chain. And then I can keep doing this. I can put this 8 and 9, and I can put it at the end right next to this 2, right? And I just continue this chain over and over, and I still have the ends here, this 9 and this 1, they can still be next to other things. Or otherwise, if I run out of things to put, then essentially 9 and 1 will just be next to each other, and there we go, we just have a giant circle, right? So that's kind of the end. So you essentially always have 2 ends that you can connect stuff to. So every single component that has a length 2 cycle, you can start connecting them all with one another. And the best part is if you have something like this. Here, if you have a length 2 cycle from this 11 and 10, well, from the 11, I can connect anything to my left and 10 to my right, right? But here's the best part. I can say, okay, from this 11, I have this 12 and 13 here, right? And from this 10, I have this 14. I can consider this as one big component and connect that. Like, for example, here I had this 9 and 1. I could connect this 13 to the 9 here and this 14 with the 1 here. So I don't have to just connect this length 2 cycle over here. I can connect this length 2 cycle as well as the things that come here and here. So what I can do is from this length 2 cycle, I can find essentially with reversed edges, right? Here we'll reverse the edges, which is why we build an adjacency list where it's like instead of appending favorite of I to I's neighbors, we append favorite of I and have I as one of that guy's neighbors. Here we'll reverse the edges because that way, essentially from this 11, we'll say, okay, what is the longest path backwards that can go from this 11 where I don't go to this 10, right? Because I don't want to obviously go this way, right? So what's the longest path away from the 11 that doesn't go to this 10, right? Grab it. For this 10, grab the longest path that goes out of this 10 and not through the 11 here. So like in this case, it would be 14 because again, we reverse the edges, but even if you reverse these edges, they still exist. So you got to make sure that you don't go to your, like there's a length 2 cycle, 2 nodes in that length 2 cycle. You cannot go through one another, right? Because the point is like, you know, the thing, like if this guy's on the left and this guy's on the right, it's like, okay, keep connecting things to the right, right? And here, keep connecting things to the left, right? If here it's like, you know, I have a length of chain 10 million, right? I don't want to be like, oh, this guy also has a length of chain 10 million if I go there. No. I can connect only things that are away from this 10 and from this 10 things that are away from this 11, right? But the point is that I don't have to limit myself to just connecting that length 2 cycle. I can connect like whatever's the longest path from this guy backwards, the longest guy from this guy backwards, including these 2 nodes together, and have that as one full component and connect it with another length 2 cycle, or just have it as is alone, right? So that's a very, very powerful thing. So there are 2 types of components, one with cycles, where the length of the cycle is greater than 2, which is like, okay, I can only have the employees in that cycle in there, so I'll consider that as a valid case, but, you know, and so, like, I'll always, you know, augment my res. So, like, the point here is, like, you know, initially, I have every single node unvisited, right? And while, you know, I still have unvisited nodes, I'm going to pop an unvisited node, and here what I do is, like, okay, essentially keep traversing, because again, every single component must have a cycle, right? We already talked about that. So here I'll essentially keep traversing from that node over and over and over until I reach a node I've already visited, which will essentially be the cycle, right? And the nice thing is that essentially for every single node, I will keep track of the time stamp, or like, you know, the amount of distance I traveled before I reached that node, right? So here when we pop a node from unvisited, it took us 0 time to reach this original node. Now we'll say, okay, current distance is equal to 1 for the next node. And so here we'll say node is equal to favorite of node, right? And then here it's like incur dist is equal to 1. Here and so here we'll say, okay, while node is not a node to dist, then it's like, okay, first of all, if it's not an unvisited, then it's already a cycle that we've seen. So it's like, you know, we've already computed that, so we don't need to compute it again, right? That's for later, not really important. You can even remove this, right? If I remove this, I'll still have a working solution. It'll just be way slower. Yeah, so here I need to do discard because again, I won't have considered, oh my gosh, I won't have considered cycles that I haven't already yet seen. Or I mean that I have already seen, right? So now if I submit it this way without short circuiting when I've already seen a cycle, you'll see that it works. It's just very slow. But that way it's like, you know, if I've already seen and computed, like, you know, the results for a certain cycle, I can essentially be like, oh, okay, that's completely fine here. And that way we have, like, you know, a much faster solution, right? But that's just like, you know, a short circuiting detail. Otherwise it's like, okay, we're going to remove that node from unvisited because it's like we're visiting it in our current traversal. We're going to say, hey, this node, it took this much distance to reach it. We're obviously going to augment that current distance by 1 here, and essentially say, node is equal to the node, the favorite of that node, and augment our current distance by 1, right? And the point is that we're going to keep going through this while loop until we see something that is indeed in our node to distance, right? Which means it's like the very first node that we revisit again, right? Which means like a cycle starts there. And so here, as long as we've not already seen a cycle, we'll say, okay, we'll grab the length of that cycle, right? So essentially the way we'll do it is essentially for every single node, we marked, you know, how much distance it took to reach that node. And at the very end, we have a current distance that we have. And at this current distance, we just revisited a node that we had already seen, right? So we can essentially take, like, you know, how much time it took to get to that node that we already saw the first time, and subtract that value from the current distance, right? Because that difference will essentially be one full iteration of that cycle, which is the cycle's length. So we store that as the cycle's length, and then now it's just game over, right? Whether it's length 2 or not, we essentially know what to do. If the cycle length is greater than 2, then we know, okay, we can only have those employees in that cycle together and nothing else in that not only in that connected component, but in the entire graph, right? Because again, they all already have 2 predetermined seats next to the 2 of them inside of the cycle, so we can't add any more employees inside of there. So here we'll just update res with the cycle length, right? So if the cycle length is greater than 2, that's like, okay, we can have, you know, all the employees in that cycle together. So if that happens to be the greater solution, then that just happens to be the greater solution, right? So here we'll say, okay, if res is less than the cycle length, then we'll update res to be that cycle length, right? So we'll set res to be the max between its current self and that cycle length that we just found, because only the employees in that cycle can be together, and then we'll continue to the next thing, right? Otherwise, if the cycle length is 2, right, here I just commented out my assert, but here it must be 2, because again, there's no length 1 cycles, because no employee points to itself, as described here by the problem statement itself. Here what we will do is like, okay, remember what we're going to do is essentially we're going to say we're going to take our length through cycle. For example, here this 11 and 10, and we'll be like, okay, let's BFS to the first thing away that we can see with our thing. Oh, by the way, this might be another thing that we can do. Here we'll do stack is equal to just 0, cycle node. And here we'll say stack.pop. Does this work? Yeah, we can just DFS instead of BFS. That way we use a list instead of a collections.deck. And yeah, nice. It makes us a little bit faster and so on. Whenever you can use a regular array instead of something like collections.deck, a dictionary, whatever, and so on, usually makes your things faster. So I like doing that whenever I can. Okay. Right, we can also do I won't make my visit set like, you know, a Boolean array or so on. Like at that point, this is just excessive, but like, you know, little quirks like that, I'll do. Right, but the point here is like, okay, we'll take this, and here we'll essentially, I had BFS before, now I'm just doing DFS. I'll DFS essentially with reversed edges, right? We have an adjacency list with reversed edges, right? Because here essentially we want, you know, the longest path to reach this 11, that it doesn't go through this 10. And then for this 10, like, you know, the longest path that reaches this 10, which is the same thing as like, you know, flipping the edges and being like, okay, what is the longest path from this 10 onwards where I don't go through this 11, right? That's kind of the idea. That's why we reverse the edges. But the point is like, you know, from this 11 with reverse edges, what is the longest path without going through the 10, because that's the other node in the length through cycle that I can reach from this 11, right? Because I'm going to greedily, you know, get the biggest chain that I can get and add that onto, you know, my components of length through chains, right? It's like I'm going to get the biggest thing I can from this length through chain, same thing from this one, from this one, from this one, and then add them all up, and I'll chain them all together into one huge chaining of length to longest components, right? So here's like, you know, the longest cycle of length to component that I can get is like, okay, from this 11 I can reach this 12 and 13, from this 10 I can reach this 14, so I can do 13 to 12 to 11 to 10 to 14, right? So that'll be a length 5 component, right? And now this 13 and this 14 are essentially free to be chained, right? Now for something like this 3, 2, here there's 0 nodes away from this 3, here there's 0 nodes away from this 2, so these are the ends with nothing to the left and right of them, right? But again, I can chain this onto, right? For example, I can connect this 2 with this 13, and now we'll have 14, 10, 11, 12, 13, and from this 13 to the 2 and 3, right? And then this from this I'll get the longest possible thing. Here for this one, the longest possible thing was like, we found 12 and 13 from this 11, and we found a 14 from this 10, right? But like there's more complicated examples, right? There's a length through cycle from the 12 and 15, right? And then from this 12, it's like, okay, one this way, and then we can either do 3 and 4, but there's a better solution if we go 1, 2, 3, 4, and 5, right? So like, you know, this is the longest chain here, so that like 1, 2, 3, 4, 5, plus the 2 from here, plus 1, 2, 3. Well, here's 4, so there's 4 this way, but there's also 1, 2, 3, 4, 5, 6, so that's already better than 4. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, right? So here we'll do this 8 plus these 2 plus, you know, these 5, right? There's also these paths here and there and so on, but they're just small, right? So the longest path away from this 12 that doesn't go through the 15 happens to be this one over here. The longest path from the 15 that doesn't go through this 12 happens to be the one over here. And then we'll take the length of this longest chain, length of this longest chain, which again might be 0 for both, right? For in a case something like this, from this 1, there's a length of 0 chain away from the 1, there's a length of 0 chain away from the 0, so this is just the length to cycle component itself. Otherwise, for something like this, it's like all of this connected to the 12 and 15 plus all of this, right? So that way, it's like the way that I do it is essentially, here I have like, you know, the length of my length to cycle component. In this case, right, like for example, in this case, you know, the 1 and 0 are the things that are available for chaining, right? So it's like I can put the 0 to the end of this 13. For something like this, it's like, okay, I have this length to component. The 12 and 15 are no longer available for chaining, right? Because like the 12 is next to the 15 and 11, so it's already taken. The 15 is already next to the 12 and 5, but it's already taken. But it's like the ends, like this 18 and 17, that are available to be connected to, right? And at the end, once I have everything connected, like for example, let's say this is the only length to cycle that I have, then it's like, you know, I can just connect the 18 and 17 and we're good to go, right? But otherwise, I can connect it to more stuff, right? If I had 2 more nodes here that have before my length to cycle, I could connect 18 to one of those nodes, 17 to the other node, and there we go. We just expanded our thing by 2, right? And so that the point is that like when you have, you know, the longest component with stuff of length 2 cycles in it, you can chain them all together, right? Here I can chain from either the 18 or the 17, right? Where this component is one that had a length 2 cycle. If it had a cycle that is greater than length 2, then I can only include the nodes that were inside of that cycle. But so like an example like this, here we have the 13, 12, 11, 10, 14, and we chain it with this 9 and 8, which we chain with the 0 and 1, which we change with the 2 and 3, and then finally this 3 we connect it back all the way around to like, you know, that's 14, for example. And there we go. We have a huge circle that goes like, you know, let's say 13, 12, 11, 10, 13, so 13, 12, 11, 10, 14, 2, 3, 0, 1, 8, 9, and then to the 13, right? And that's the full circle. Again, and the point is that I took every single component that is with a length 2 cycle, breathed it out as large as I can. So like from this 11, I can go to this 12, 13, and then this 10 to 14. So I consider this as one full component of 5 nodes with a length 2 cycle. And I connect this 5 with this 2, with this 2, with this 2. So 5 plus 2 plus 2 plus 2. 5 plus 2 is 7, plus 2 is 9, plus 2 is 11. So here I have a length 11 cycle that I can build. So here's like, you know, here's like 11 employees I can have by chaining all the longest components I can form with length 2 cycles. Here's just length 4. Between 4 and 11, 11 is the biggest answer. So here in this example here, I would return 11, right? And that is kind of the point. And then in terms of the code here, it's just, you know, I initially start with the length 2 cycle components length being 2, just for the 2 nodes in the cycle. And it's like, okay, for each, you know, cycle node, which again, since here, I know that node itself, you know, I did while node is not in node to this. Now, since node is in node to this, that means like node is the cycle node itself. Since the length of the cycle is length 2, I know that the cycle nodes will be node, which is cycle node, and its favorite, right? It points to something, so and the other one must be the one that points to it back, so it's going to be node and favorite node, right? So I have my 2 cycle nodes, and then here I'll have my, okay, my length 2 cycle component is equal to 2, and then it's like, okay, for both of these cycle nodes, what I'm going to do is essentially, you know, expand as outwards as I can from that, not going through the cycle node, right? So here I always keep track of a visited set so that, like, you know, I don't go through things again. Yeah, I guess. Can I do something like this? Does this work? Yeah, I'll get rid of this. Because nothing else is going to form a cycle, right? Because there's going to be the length 2 cycle, and I can just check this, right? Yeah, lol. I don't even have to build a visited set there. Yeah. Yeah. We might as well do that. Lol. That's actually kind of funny. Here we'll say, for I in range 2, equals, so I can either be 1 and 0, so we want to flip it, right? Node equals cycle nodes of I, other cycle node equals cycle nodes of 1 minus I, or of I XOR 1. right? 0 XOR 1 becomes 1. 1 XOR 1 becomes 0. Either 0 or 1. So flip the index. Doesn't equal other cycle node. Yeah, there we go. Nice. Nice. Yeah, so the point is, so this is exactly what I meant. Okay, nice. It's just I keep making like, you know, edits to my what the heck, solution as I go. But yeah, so the point is that, like, you know, find the longest path outwards from 12, for example, that doesn't go through the other cycle node. So right, so like for every single neighbor, I can append that to my stack for more traversal, as long as that neighbor is not my other cycle node, right? That is kind of the only point. So I don't need a visit set, because again, since, like, you know, everything only has one edge and so on, I don't have to worry about another cycle, because again, every component is not only guaranteed to have a cycle, it's guaranteed to have only one cycle, right? And so if the cycle I know is with these two nodes, then I know that everything I look at from 12 will not form a cycle, right? And similar from 15, right? Because the cycle, there's going to be exactly one cycle, and the cycle is legit just as 12 and 15. So everything away from 12 won't have a cycle because it's all connected, and everything away from 15 similarly also will not have a cycle because the cycle is here. So that's why I can do that. I don't need a visited set. So that's just me being cheeky. But yeah, that way it's like, you know, I grab my cycle node and my other cycle node. Very, very, very funny stuff. Right, another way I can do is make them equal to cycle nodes and then reverse it. It doesn't matter. Right, but that's kind of the point. Stack is equal to 0 cycle node, yeah. Branch length. Alright, here we can call this branch length, path length. Get rid of the visited stuff. There we go. Nice. And now we can get rid of these comments. There we go. Can get rid of this. Want to make sure I don't have any more code. There we go. Submit. Okay, just very, very nice, very nice, very, very, very nice. Okay, but yeah, that's kind of the point. So the point is, like, you know, I'll just do a DFS reversal here, where it's like I'll always keep track of my current cost and my current node. And here it's like, you know, initially I'm at a cost of 0, and I'm going from the cycle node, for example, 12, and it's like, okay, while length of the stack is greater than 0, I'll, you know, pop, you know, the current path length and the node from the stack. Here I'm visiting a node, right, that is part of this component, so I'm gonna remove that from my unvisited set in case it's in there. Here, if, like, you know, I'll always update, like, you know, the longest branch that here we'll call this longest path length, longest path. If longest path is less than path length, longest path is equal to path length, right? So every single time I find a new path length from 12, it's like, you know, if it's greater than my current longest path length that I found so far, then I'll update it, right? So that way, like, you know, I'll end up finding, you know, what is the longest path from 12. And the point is, I'll visit every single thing away from 12 that is not going through the 15, right? So, like, for every single neighbor in the adjacency list of the current node in my stack, if the neighbor is not the other cycle node, then we'll append that into my stack here, right? So one way, yeah. So that's the point. One way I could do is essentially like, do the hard code the case for the cycle node and then go from there, because I know that I won't be able to go through the other cycle node again. But yeah, it's fine. But yeah, so the point is like, I'll keep expanding through my neighbors as long as my neighbor is not the cycle node, because I know I still have an edge to that cycle node even after I reverted all the edges by definition of a cycle, right? 12 points to 15 and 15 points to 12. When I reverse it, now it's just 12 points to 15 and 15 points to 12. It's the same thing. So I'm gonna make sure that I don't go through, but right, because the point is like, for example, here 8 is definitely much better than 5, right? So it's like, oh my gosh, if I go this way, I go 1, 2, 3, 4, 5, 6, 7, 8, 9. But the point is I can't do that, right? I want to have 18 and this 17 be the connected ends for the next one. So I need to find the max path away from 12 that doesn't go through 15, and the max path from away from 15 that doesn't go through 12, right? And that way it's like I have a component of maximum length, including the length through cycle, that I can then connect and chain with other longest components that include length 2 cycles as well, right? So here I'll say, okay, length 2 cycle component for each cycle node, I'll get the longest path away from it, and I'll add that value to my length 2 cycle component, right? At the very end, once I've gone through both cycle components, my length 2 cycle component initially was of size 2 for these two nodes. I then appended the number of nodes and the maximum path away from 12 that doesn't go to 15. I then appended the path length of the longest path away from 15 that doesn't go to 12. So now I basically have these two plus 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5, 6, 7, 8, right? So I have 8 plus 2 is equal to 10, 15, right? And like this length 2 cycle component will be 15, right? And now the thing to realize is that I can chain this with other longest components that include length 2 cycles, right? So if I found another one like this and so on, I could connect the ends of this one with the ends of that one, right? So here I'll essentially have a global variable that is my length 2 cycle chain, because everything that has a length 2 cycle, I'm going to first find its longest chain. For example, here was like 15, the way that we talked about, and then keep appending that to this length 2 cycle chain value, right? Because every single longest component that I find that includes a length 2 chain, I can again chain those together to form one behemoth group of employees, right? For example, here it's like, I had 1 of 5, but I can chain this with this length 2, chain it with this length 2, and chain it with this length 2, right? I can essentially chain them all together, right? To form one group, one huge group of employees, right? And then at the very end, essentially res will be the maximum of my closed cycle lengths. Length 2 cycle chains will be all the length 2 cycles all chained all together, right? And so at the end, I just need to return the max of those two, right? So here I say, okay, if res is less than, res, which represents, the maximal cycle length out of any cycle that it was of length greater than 2. And then if it's less than, the length of all the length 2 cycles all chained together, in terms of length, then I'll set res equal to that and then return res, right? So the point is that I'll return the max between res and this. And so, okay, if res is smaller than this, set res equal to this, right? Yes, right? So, or here, yeah, and return res, right? Another way I could just do is just return this, right? So the point is return max of res, length 2 cycle chain, right? Maybe that just makes it a bit more clear, right? I usually don't like doing max just because it's slow, but here in the last case, it's completely fine, right? So there we go, bada bing, bada boom, and hopefully that solution makes sense. But yeah, I will again admit that I did have to look at the editorial, although I feel good about it because it's I essentially read up to a certain point, and once I read everything I needed, so essentially I stopped reading right, kind of right here, right? Wait, a cycle length, which we compare with the large. Yeah, okay, this is where I stopped reading. I stopped reading right here. So I read everything all the way up to here. So I started looking into approach 1. I read everything all the way up to this bullet point, and then after that I stopped, right? And then I didn't read this. I didn't read the algorithm part. I did not look at the code of the solution, but I did end up reading everything in the tutorial up to this very first bullet point from approach 1, right? Including all of the stuff in here to help me build the intuition for this problem. And honestly, thank goodness that I did, because God knows how long this problem would have taken me if I didn't look at the editorial. It's already multi-hours long, and that's because I was solving it with the editorial, which is just absolutely monstrous. But honestly, I'm glad that I did, because I learned a lot. It's a challenging problem, and we conquered. So honestly, this is not a defeat in my eyes. I know at this earlier point in my video I said, like, you know, this is the biggest fail of a daily I did. Honestly, I'm content with this result. This is a good learning outcome at the end of the day, even though I wasn't able to solve it completely on my own, without looking at the first half of the editorial until I didn't need any more help. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or a comment. Well, otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.